Okay, lesson 9.6 is identifying symmetry. Now, you talked about symmetry in Algebra 1 when you had the axis of symmetry in a parabola. And basically, that was that line that went right through the center of the parabola, cutting it in half. Okay, well, symmetry basically means you can split something in half so that it's a reflection of itself, so that the two sides are a reflection. So in this particular situation, that's line symmetry. So let's go ahead and define it. A figure has line symmetry. A figure has line symmetry if the figure can be mapped. If the figure can be mapped onto itself by a reflection in a line. Totally botched up that. By a reflection in a line. Okay, so this terminology, mapped onto itself. So if you look at these two rectangular boxes right here, okay, if I were to fold this, those would be mapped onto themselves so that these lines are folded together, these lines are folded together, and these lines are folded together, touching, so it's mapped onto itself, and it's exact reflection from one side to the other. So now then, if we're looking at images and we want to determine how many lines of symmetry that the figure has, you got to look and see how many ways you can cut this in half so that it reflects. Not just cutting in half, period, guys. It has to be cutting it in half so that it is a reflection. Now, this rectangle has two lines of symmetry. I can cut it in half this way so that it reflects this direction. I can also cut it down the middle this way so that it reflects itself here. Now, you can draw a diagonal in a rectangle. But if you were to draw a diagonal, it would cut it in half, but it would not be a reflection of itself. So you can't do a diagonal for a line of symmetry. So this particular image has exactly two lines of symmetry. All right, now then, in a pentagon. All right, if I were to draw a line through that vertex right there, you can see that this side is a reflection of this side. And if I were to do that through every single vertex of the pentagon, the left side would be a direct reflection of the right side. So I'm just going to go through and draw a line through each vertex, okay, splitting the pentagon in half. When it's all said and done, I drew 5 lines because I drew a line through each of the vertices. Okay, so this one has 5 lines of symmetry. Now, that only worked because this was a regular pentagon. All the sides were the same, all the interior angles were the same. Now, if you look at this pentagon, it's not regular. You've got these two angles are the same, and it looks like maybe these 3 are, but I can only draw one line of symmetry right through the center, and that is the only one that it has. If you were to turn it this way and I were to draw a line through this vertex, it would not be a reflection of itself. You could see it's kind of warped. So this particular pentagon only has one line of symmetry. Now, when we say line of symmetry, we're using it as the line of reflection. Okay, so your line of symmetry is the mirror. It's the point that all the points on one side reflect across to the other side. Now, rotational symmetry. This has to do with a figure, a figure that can be mapped onto itself by a rotation of 180 degrees or less. Okay, so we're going to take a figure and we're going to turn it, rotate it, and we have to turn it somewhere between 0 and 180 degrees. Now, every figure has 360 degrees rotational symmetry. If you need to jot that down, do so, okay? Because I can turn anything, okay, 360 degrees, and guess what? It maps back onto itself. But we're trying to see, can I turn it 90, okay, 180, and then if I can turn it 90, I can turn it 270. And if I can turn it 180, we definitely know we can turn it 360. Okay? All right, so now then, does the figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. So looking at this, okay, I've got a square, okay, and so every angle is the same degree and every side has the same length. So I can rotate this angle 90 degrees to right here, and then rotate it to right here, and then rotate it to right there, and then rotate it to right there. So basically every 90 degrees this image has rotational symmetry. So I'm going to take 360 and divide it by 4 and say that my rotational symmetry is every 90 degrees. So 90, 180, 270, and 360. Okay, now then, a hexagon, and it's a regular hexagon, meaning all angles are the same and all sides are the same. So in this one, I can start at this angle right here. I can rotate to this angle, and this angle, and then to this angle, then to this angle, here, and then back to where we started. And so since there are 6 different angles I can rotate to, my rotational symmetry will be every 60 degrees. Okay? So 60, 120, 180, 240, 240, 300, 360. Every 60 degrees. Now then, a kite. Okay, if you remember, a kite has congruent sides, side by side, here and here. And it only has one pair of congruent angles. Therefore, if I rotated this image and I mapped this angle onto this angle, that would be a rotation of 180 degrees. But these two sides here are not congruent to these two sides, and these sides here would be mapped on to these down here. Since they are not congruent, it would not have rotational symmetry. So this has no rotational, give me an O there, rotational symmetry. Okay? And I'm sorry, the center of symmetry should not be there. Just scratch that bad boy out right quick. All right. On down to the next one. We're going to check and see how many lines of symmetry does each of the figures have. Okay? Well, if I were to take this trapezoid, isosceles trapezoid is what it looks like, and split it down the center this way, okay, this left side would reflect over to the right side. However, I cannot split it this way and have it map as well. So this particular image only has one line of symmetry. I can't do diagonals because they are not reflections across diagonals. Okay, this one is a square. All right, so now be careful. This one can kind of trick you. I can draw a line of symmetry through these angles right here, and I can draw one this way, splitting it in half so that it reflects across this way, that line, that horizontal line, and across this vertical line. But I can also look at a square and cut it in half this way, just like we did the rectangle in the earlier example. And this way. So what I end up with are 4 lines of symmetry. Okay, now let's look at this last one. We're trying to determine if these have rotational symmetry, and if so, describe any rotations that map the figure onto itself. All right, this I believe is a dodecagon. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, now I have to turn this a total of 90 degrees to be in the very next quadrant, okay? To go from horizontal to vertical to map onto itself. And each one of these will map onto itself because they are all the same length. And these little niches will map onto the niches down here below. So basically, you would take 360 degrees and you'd be able to rotate this 1, 2, 3, 4 times. So this figure has rotational symmetry every 90 degrees. And in this last one, number 4. Now, this appears to be an isosceles triangle, meaning these two sides are the same and these two angles down here are the same. Well, all right, since I have these 3 angles, I should be able to rotate this angle down here if I have rotational symmetry. So it'd be 360 divided by 3, or every 120 degrees. However, this angle is not congruent to this one, nor is this side the same length as this side, and this side would be mapped onto this one if I rotated it 120 degrees. So therefore this image has no rotational symmetry. If it were an equilateral triangle, then yes, it would have rotational symmetry every 120 degrees. But because the angles are different, it does not. All right, so those are your 2 forms of symmetry that we're looking at. Line symmetry, where you can cut it in half and it reflects. Rotational symmetry, where you can turn an image and it maps directly back onto itself with corresponding sides and angles that are congruent. That's it, guys. Thanks.